Our next presenter is Tejas Patel, who is a senior software developer at Amazon. And Tejas leads the work on seller performance and order experience for retail, including AI-driven systems. And he is experienced in fraud detection. And that would be his presentation. Tejas, tell
Yeah,
us more about yourself and about your work.
awesome. Thank you, Jacob, for introducing me, and thank you for inviting me here in DecisionCAMP. So, as Jacob mentioned, I am a senior software engineer at Amazon. So I can tell something about the work that I'm doing. Um, so I work so whenever someone visits an Amazon, they go to product page, um, and then they basically see all the products, their reviews, they put it in the cart, and so that piece I like basically I like lead that piece. And so all the pages where the people just do a window shopping, those pages, and when any customer like already bought the product from the sellers and now they have some issues like returns, refunds. There are so many different kind of claims that customers do. There are so many fraud happens between the customer and sellers. So basically today we manage like 10 million sellers, and the whole fraud cycle of worldwide 10 million sellers. This is like a 10 million seller of figures, but it's more than that. And based on my experience and the journey that I have been through in Amazon in last 6 years and totally like 10 plus years in the software industry, um, the presentation is about my experience. I wish I could have done some demos, but based on the policies, I cannot like basically display any design. I wanted to basically present a system design to give more understanding of what we do. But on some other day, if I get approval. But today, based on my experience, I have created this presentation. So the journey where we had a traditional system, which is trying to identify the patterns for the fraud, and now with the integration of machine learning and like the custom models that we have, like Amazon has created, like in Amazon Bedrock, and we also have the contract with Claude, which is public. Um, so I just want to discuss few pointers here, and then happy to have the conversation with other folks. Hope this helps and I can contribute positively in decision camp. So I'll start with a number. So like every single second, like somewhere in the whole entire system, um, like basically somewhere in the world, a company like that one I work with have like 10 millisecond or 10,000 of seconds of decisions they have to make for each transactions, whether it is like fraud or not. So like the transactions are like it is very fast. Like 10 millisecond is still like on P90. It means 90% of transactions are faster than 10 milliseconds. So decision has to be fast enough so that customer never notice any delay, customer never notice um, any kind of bad experience. So it has to be right enough. And we have to basically check all the fraud signals or all the fraud decision rules between that. And we cannot be aggressive here, because if we become aggressive, then the legitimate customers will be affected. So it is a very thin line, or you can say very narrow bridge that we are like going on. It's a journey where we cannot be putting hard and fast rules. So today I want to talk about something um, that industry had some wrong directions in the beginning, the history, and like one of the direction that I want to talk about. So so the fraud patterns that we wrote today are now based on machine learning. They basically end up with the black box today. So like when we use a machine learning is simply an inference. So now we don't know. the training that we did on the machine learning models, how that is affecting our decision. So before the AI, we had all the different business rules that we were applying into our systems. And those rules were written based on the leadership approvals. Those rules were written based on the past historical analysis. So there is an analyst who is sitting there, is trying to query different databases, is trying to query and create some different charts and metrics. And based on that, the second step is we do the business decision, and then those rules are applied to the fraud. But today, and also in this, the whole piece, the regulators also come into the picture. For example, the EU region has different rules than North America, so they have more scrutiny, more regulatory rules, and we have to consider all of them when we are trying to design this rule. Um, so today, when we use machine learning, we can train the machine learning models, but we don't have a full control because there is an inference which gives an output, and that basically do a decision because we want to automate everything with the help of machine learning. So we have to take that dip of having some kind of black box that AI is doing, but we can also like track and trace everything. It's like I believe everyone has heard of word called observability. So we can like basically monitor all the decisions of AI, and but we cannot be proactively changing the rule because it's a model. We have to train, we have to create new version, we have to see what are the disadvantage, what are the decisions that ML did wrong. So I want to talk about not the fully static rules that we had, not the fully ML, somewhere in the middle, which is an hybrid architecture, where we also use the rules, where we are also using machine learning.
Tejas, I'm sorry to interrupt. You're not moving your slides. That's in purpose, or
Um, yeah, yeah, actually, I'm just giving some kind of
okay,
introduction,
okay,
but
no
then
problems, no
when I can,
problems.
um, yeah. So basically, the intent here is to have the hybrid, like we'll also use rules and models. So let's jump on to the slides. Just- Okay. So I'll basically give some examples of our team on a high level, but this is just my introduction. So I already talked about it. I'm also a researcher as well. So I basically do a research on applied AI and also how we can optimize the AI inference. Like today, before we jump on the actual things, I want to talk one more important thing is like in last 2 3 years when we are trying to implement the AI in our systems, when there is a scale, when there are like billions of billions of customers are visiting the Amazon every day, there is a scale, and if you want to implement an AI, it comes with a cost. I know the token value. The AI cost measures with the token, and the token value is going down day by day because it's costing them billions of dollars. There are some public figures that we are seeing in last 8 to 9 months or a year cap. Uh, like they are doing an expenses on AI, a lot more expenses. So the bottleneck that the we are facing right now is the cost of in like running the AI versus using the traditional system. So when we are switching to automation, we are switching to ML models. It is costing a lot more than the previous system to all the companies. Even though I know that AI, when the AI is there, they don't need like for example, there are 100 people, they might need 80 people, but the cost of running an AI is more than those 20 people that they don't want, or they basically want to automate. They need less people, less engineers. So they are figuring out how to basically handle that. And so there is one of the research area that I came across, which is like how to optimize the costing of AI. So that's what I do. Um, so this is an agenda. So first we'll start with the problem, why fraud detection at hyperscale and why it's a problem that we're trying to solve, why it's a hard problem actually. And before we get into architecture, I want to spend a few minutes on the cost, which uh which will be an interesting thing. And then I will talk about rules versus ML. Then we'll talk about the architecture, like how this hybrid architecture will work with all different components and decision flow. Some examples I'll give from the the order experience at Amazon order experience and some production discussions that we'll do. So let's jump into it. Um, okay, so let's start with the scale. Um, so the number itself says it has to be very fast. um, we need a distributed system where we can have lot more transaction in parallel on multiple threads, and we can't afford like a delay or the failures because it will actually snowball into a lot of problems. So why does here like we are talking about the scale? Because let's say if there are 10 millions of customers, they're trying to, if they ordered something and there are some of the sellers who are a bad actors, and like there are a lot of customers will be affected within an hour. We cannot roll back directly because fraudulent sellers can basically take a lot millions of dollars from the people in the fraction of a minute, because on the platforms like Amazon, they're selling not to like 10, 20 customers, they're selling worldwide to a lot of customers. And nowadays, um, there are a lot of sellers who onboard every day. So we can't say that, okay, if the seller is new, we shouldn't trust them, but we have to interactively identify like why this seller is fraudulent and why not the other one. Um, so so there are two completely different paradigms, like making the decision and like each fail on its own or different reasons. So like basically what we do is we have a rule engine which is basically written and reviewed by humans. Another is like a ML model that learns the patterns. Now we have like 20 years of historical data that we feed to the model. There are AWS services that we use like the SageMaker, the Bedrock, and we basically have the publicly available models that we use, and we have our own models. So like Claude, GPT, the the corporate version of those models are deployed, and we basically go and feed our historical data to that. So it's in combination of both, that our tested rule engine versus plus that behavioral pattern that we are getting out of the historical data. And so this both basically combines and create a pipeline, and it gives an unique score for each seller. And based on that, we decide what we need to do. Um, so I want to so this decision is called an explainable decision. So I want to talk about that explainable word. Like in fraud, uh, in the era, like I mean, in this area of fraud, um, we have to be anything that is regulated have to be fast, and it has to be right, but we don't want to be like 100% right. And basically, the problem is we have to, whenever we decide that something is fraud, we have to have that reasoning for the customers, for the regulators, for everyone. So this is more about we have to provide each and every reasons why we have blocked some sellers or why we have blocked some ASIN, like the product. So that is one of the important thing. Um, so the cost. Um, So there are three things we can do here. Like the thing that I was talking about is a balance. Before we get into anything else, like different components, I want to talk about this. So if the system, the first is too loose. If we allow um, all the sellers, and that if there is some fraud signals that we are ignoring, or we are saying that we are not enforcing, then it will be too permissive. Like the frauds will be detected, but there is no action that we'll be able to do, and it's just sitting there. We are seeing in our metrics, but we are not doing anything, and all the fraud transactions, actually it will went through, then customer will come back, they will ask for the refund. So there will be a lot of contacts from the customer, a lot of chargebacks that any company has to deal with. So not enforcing and being loose will eventually have a lot of frictions with the company itself, because they have some the big support team. They will talk to all the customers who went into the fraud, and they have to analyze each case, and they have to give the charge back to them. And so it's definitely gonna cost company a lot more things. So for example, um, I think I can give an example of the recent year where we had like one of the problems. I can just talk about the high level. There are a lot of companies who don't sell on Amazon, but people who buy from those companies and they start selling on Amazon, and they say, okay, we are an authorized seller of that product. For example, a Nike, but they're not an approved seller, but they just start selling because the original seller is not on Amazon. They're not selling it. So it's like an they are doing an identity theft. They are basically impersonating themselves as an authorized seller, because there was no checks on that. There was no audit with the actual company. Uh, so that was one of the fraudulent way of some sellers selling things. So there are a lot of loopholes that people identify, and this is one of the example where if something goes wrong, people like customer sees this as okay, um, like this is an Nike product, so they trust blindly because they know that the company has a value and the same company is selling here, but it's not the case. Like it's some other party sellers who are trying to sell after buying in the bulk. So those are the bad actors is one of the example. Now, if I go and say, oh, okay, let's make the system like too strict, then we are blocking a lot of people. Let's say today I say, okay, no one can sell a product without an authorization. Then they lot of genuine customers, sellers losing their listing. Not all the companies want third-party sellers to, not sell, because they basically there is one company who likes to who are basically allowing others to sell because it's their product and it's more marketing, and people will use more products of their company. So it's like the double-edged sword. We can't say, okay, from today we'll close it out. We'll put down all the listings who are not authorized. We can't do that. So we have to find a middle way, and basically we have to explain to our customers and sellers that okay, this is what we are doing, this is our rules, this is our policies, and we have to go case by case. Now the third is system is too opaque. Like if the failure mode specific to ML, you can be operating at exactly the right sensitivity, and basically not only looking at one signal, but looking at holistically for that particular customers and the seller's history, and also having a different workflows which helps us with what is the, for example, the reviews is one of the signal that how customers are giving feedback to the seller. So we have to basically have the threshold on different components, and we have to holistically decide that, okay, even if that seller is selling without authorization, how much likely that seller is doing a fraud or not. So that question can be answered, but it has to be monitored, and it has to be on a some on a line where we are not getting anything bad reactions, or it's not too loose or strict. So that is the challenge here. And when the machine learning comes into the picture, it becomes more on the edge, because we don't have a full control over what ML does, because all we can do is we can train them, we can basically test them, and but at the end, ML will do the decision. The model will go and say, okay, we are enforcing or not. That the final action the model will do if you want to automate it. So that's where the challenge comes up. So the solution is to have the basic combinations of both. Like we have to say, like once the ML decision comes up, and our rules that we put on, and then we do human checkpoints in the middle, and then we have a different system that we have just built to monitor all the decisions regularly, like check-ins every 24 hours. So that's the thing. So I'll continue with the weaknesses. So now imagine there is a system sitting there. It's a small tiny microservice which is there reading all different requests, trying to see, okay, when someone add a new listing on the seller dashboard, it will basically check all the rules and say, okay, perfect, this seller is good, this product is good, it's a unique ASIN, and there is no flags for this seller, there is no flags for this particular product itself. And our system logs it saying, okay, this listing is approved. Yeah, we put it on the Amazon. Now, now the seller itself, the bad actors are also in seller. So they will understand, okay, if I put like this, um, our listings are getting approved. So they will easily, so rule engine basically is very fast, because we have set of rules, we have set of systems that will just proactively decide that this listing is good, and it will approve it. But it will actually expose a patterns to some bad actors. Now, when we jump to models, um, it's not proactive, it's a reactive. The first thing, it's reactive. It will take this little bit of time, says, okay, after 3 or 4 days, it will basically decide that, okay, do we need really this listing is good or not, first thing. And then the parameters of ML is going to change based on, so it's a reinforced learning. So when something we audit and say, hey, this is wrong, we feed back to the model, and model will understand, learn it, put it into the model skills, and based on that, it will say, okay, now my decision will change. So it will adapt everything that we are saying. Rule engine also we can adapt, but it has a lot of hops. It has to go through a lot of audits. There are a lot of people sitting in the middle. It's not straightforward, but models can adapt easily. Um, but we have to observe a lot. Model decisions are a little bit more complex, and little bit we can't predict 100% like rules. So now the combination, what does it mean actually? Like why we are talking about combining both architecturally? Um, Neither we are just not just running rule or not just running model side by side. We create this, basically it's a three-layer framework that we are using. So I want to walk you through, but so there is a so first layer is rule. It's eligibility checks and the constraints that we add. the job of the rule is to answer the question, is this transaction even scope of behavioral scoring? Does it violate any non-negotiable uh, things like not want to go into those rules, but the business or legal constraint and anything that for this particular country or this particular marketplace, is there any caps or anything that we cannot sell? And is this merchant categories? Is simply if that merchant can sell this item or not, because some things need license as well. So we have all different policies, we have all different checks. And basically it's a deterministic, like it determine at the end what will be the result, and we can also trace back like something. Okay, if the system gives the answer that okay this is eligible, then we can trace back, we can go through the whole code and different systems source of truth to, like, from the request to source of truth, we can trace everything, like why the system decided. The layer two is the mammal model. Basically, it doesn't decide, it gives a score um, of that risk, like why it's fraudulent score. So everything that passed the hard constraint in that layer, but still needs some judgment call that okay, after the rules also, we are seeing that we are not able to enforce fraudulent sellers. We still have some kind of risk, which we have in the legacy ones. So then it goes to ML model. ML model takes a judgment call based on the score that it gets from the patterns. It also looks what engine has does, and based on all this and all past billions of transactions that he already has a knowledge, it gives some score. And the third is orchestration. Orchestration is, I think I think it's the glue for all different systems, the management layer. So this layer basically, say like a final decision or critical layer where we do combine the ML score and we have our rules. We both combine it, and there are two things we do. First is we audit what all rules and ML model components did, and we also do a manual review. Not all of them, but some of them we do a manual review, and and then we basically give the output to the actual system, which decides and execute it. So so I want to say you can say that it's immutable in terms of decision, because once we decide, we cannot roll back until something goes wrong, or once. So basically they have to challenge, like seller or customer, they have to challenge like why it's not, why the listing is not there, and then they have to provide an additional evidence. So until then it's immutable, and we can also feed back if something is challenged, and if we see okay our decision was wrong, we can always feed back into our ML model. So the current score that orchestration layer generates is the final score, and it basically goes to the seller. Um, so the goal here, like the reason I'm talking about all this, the goal here is to understand like all the decisions of the fraud is explainable, and it's a combination of different iterations. So it has to be more accurate, and today I think in our systems we see a lot, like good amount of percentage of confidence in our fraudulent cycle. So that's one thing. In the interest of time, I'll go a little bit faster. So so this is a pipeline I want to talk about stage by stage, and what we what is happening here. So because of the first is ingestion. So ingestion is then event stream. So let's say, so when we are designing a system for 10 million customers, let's say there is a small company which had only 100K customers, or you can say like 10,000 customers. Now they suddenly are very popular and they are now like having 10 million customers. So they have to design in a system in a way that is not always in a sync. They have to make an async design where um, they cannot take any every decision or like in a within a fraction of second. They have to decide which decisions need and fraction of second decision, which decisions can be done in later like 24, 48 hours. So this is one of the decisions that we can take later on in some of the cases, like listing all, they don't have to be very, very fast. We have to have more due diligence. So first is um, all the all the requests that we are getting for listing, for example. Um, we basically collect everything from the event stream. Event stream is something basically works offline. It event stream is a it's in queue where every all the requests will drop in, and the system will take their own, his own system will take own sweet time to process it. So that's an entry point, the transaction ingestion. Um, so transaction every transaction enters into transaction ingestion, which we call an event. From that event, we derive feature in real time. So what is a feature? Feature in the world of AI, the feature is like what are all the parameters of that listing, like all the data values that we can derive it individually from that particular transaction or that particular data. It's like a schema for AI. Um, so we gather all those feature, and I think there are like in a Kafka Kinesis are like one of the famous components that teams uses everywhere. Um, we want to we want to like skip all the real time reactions. This is like a separate, it basically do an isolation. The systems, when any data comes into the ingestion layer, it isolates the whole system from the real time things. For example, if you want to, if you're clicking on buy now, calls the credit card company providers and do the transaction, and the order is placed within a second. But this system is isolated. We can't wait um, for the transactions to happen. We can't wait for any fraudulent checks to do. Like we can enforce fraudulent check after that transaction happens because we can't do it in real time all the way. Um, Stage two, like once the feature is gathered, um, we basically put it into the database. So it can be a vector database is one of the recent example where create a vector so that AI can understand properly. Um, it creates a relevance for AI easily. Stage three is rule engine, where it basically the engine that is having the written rules, legacy rules, and new rules the way we were operating before. So that component is also we'll pass it through. And then the stage four is the transaction that pass through an ML scoring service. So now um, the feature store gathered and based on an ML rule engines are applied, and now the ML will calculate the score. And then the fifth layer is arbitration. We can do overrides as well. Like one of the thing that I forgot to tell is we can override some if there is an escalation. Let's say some seller is a very big seller, and I mean our fraudulent decisions are affecting that seller, or and they come to us say, hey, we really think that this is not good. Then we review everything, and we can also override our policies in a real time to de-escalate the situation, because we can't wait for systems to go through all the workflow again. So we have to basically, it's like a kill switch that we have. And then the last is decision and auditing. So that is like a very standard thing. Um, but um, in the auditing and decision, I would like to say, it's not simply logging what model is doing. So in auditing, we have to audit like what ML did actually, like what parameters ML computed, what inference ML did, and why the score was, for example, the confidence score of ML model is 95, 0.95 out of 1 for this transaction to be a fraudulent, then why is that? Like, what are the things that ML did? So those things we have to audit, which is very indeed for um, like different regulators. So now I would like to talk about the latency actually. But before so latency budget. So um, when we had a rule layer, we were able to identify everything within a second, within a millisecond. Now we have ML scoring that takes a little bit of time because we put it into feature store. And so today think is like that. Like for example, when you talk to Claude or ChatGPT, right? When you say, hey, can you give me the answer of this? Then ChatGPT will go into thinking mode and it takes a little bit of time to give an answer. Same goes here. It takes a little bit of time to give an answer. While if you have the static rules, the systems are very fast. They give the answer even before you realize. And now the whole pipeline collectively take a lot more time than it should. So this is what the latency is one of the things that is impacted on a scale level when we integrate an ML. So, okay. Now I want to basically talk about the one of the retail what we do here. Um, so all the things that I talked about, um, like I'm just giving one example. So when customers say, okay, I want to buy from the seller and plot like the platform that we are basically works on the trust signals. Like we call all these signals as the trust signals, which are coming from the frame, like entire system, like ratings, the feedback, like people read the feedback, right? Like what people reacted on that product and seller's history, like how many orders the seller fulfilled, how many orders were charged back, all those things. So those are like it's called a trust signal. Each and everything called a trust signal, and we combine everything. I think it's a standard for all different organization, but I'm just giving an example. Um, so based on that, we do a detection of fraud and for example, a review. Why it is called a trust signal? So review, any customer can only submit a review if they bought a product from that seller. They can't put a review without buying anything. So those are like verified purchases. Um, but seller can't just buy something online saying, hey, I need 5 reviews, I need 10 reviews, or I need high rating. They can't do those things. So these are like actual trust signals and we can rely on for deterministic decisions. Um, so on top here, we are saying that we are putting some relevance with the ML. So ML also use all these trust signals to create a relevance between different things. So rules that are written statically will go on high level trust signals. But what ML do is ML find relevance between so many things like end to end in Amazon systems. It'll go into different signals into different database and see, okay, this signal is relevant, and it will combine all the signals to compute a score. So sometimes it's accurate, sometimes it has a lot of noise. So we have to basically identify that. But it gives more basically we can ingest like more signals which are not directly relevant. Um, so today, I think I believe everyone has used Amazon Rufus as well. Like Rufus is small chatbot that pops up when you say, "Hey, this product, can you give me some different more products? Can you?" So that Rufus also works based on the relevance. That okay, if the seller is fraudulent seller, we have in our ML models, this ML model basically feed the score or not the training, but just a score it feeds into that ML. So it's like a transfer learning induced to a different ML model, and that Rufus has different transfer learnings. Um, and based on that, Rufus gives an interactive answers to the customers, um, and it gives and good accurate good answers for now, which is based on all the signals and the computation of scores based on that. So that is one of the good example as well. That how the relevance came into the picture in last couple of years. Um, I think arbitration and orchestration it's gonna be coming at every place. Um, I think credit card application is like I wanted to give some public example. Today, like when we go ahead and apply for credit card, we based on our whenever we fill our SSN, whenever we fill all different details, um, based on our current credit history, credit score, we get our decision, right? Now, what is the credit score? So, credit score is also some kind of an relevance score that talks about how that person's journey is in the financial world, how what things he bought, what that he or she has, and what other things that he or she did, like closing credit cards and defaulting on the loans. All these are being computed within like 20-25 minutes. Sometimes it takes more than that, but most of the time we people are either pre-approved because they have already computed everything of yours and market it as a pre-approved. Um, Now ML makes it more easy. So ML, when the ML comes into the picture nowadays, ML basically navigate the customer in the journey. Like ML takes all the inputs and decide that okay, this person is worthy of this credit card or not, or what is the risk there? Because the credit card companies are the biggest financial industry where they like come across fraud more than any other companies. So I think there are a couple of things I will skip over it. Structuring the rule. Yeah, I think I talked about the handoff. So today, even in the rule, when we have a rule engine, we have a support team. Like some decisions we hand off to the support team because not all the decisions are like totally acceptable what systems do. Um, but even that decisions we want to handle now. Those teams are now ML teams. Basically, all the ML decisions they have all different documentations what ML did and why that handoff come to them. So that industry is also changing, that the handoff structure is also changing for the team. So which is also an interesting part, that it's not very simple nowadays that if someone goes to customer support saying, hey, first there is an ML who takes all the input and say and gives all the directions to without any human, and if that is also not solving the problem, then it goes to the customer support. So that is a handoff. Um, I can talk more, but I think I would like to discuss with others instead of going there. Before I close my talk, I want to say the, the biggest thing that I see here in the ML industry, which is a little bit tricky right now, is the drifting. So today, when we train the model, we applying enforcing a lot of fraudulent things. Those are not consistent. Like at some point, that you see, okay, our project at launch, we are seeing a lot of automations and a lot of proactive decisions and a lot of accuracy, but it drops suddenly, model drifts, um, and models start behaving differently. And there can be so many reasons. So it's not that like if we implemented ML, we are good. It's like we have to keep monitoring and keep upgrading our version models and keep testing it, because the model drift is um, the one of the challenge that I see today when we are trying to implement all this. Yeah, I will not take too much time. I don't have anything to demo, but how I can discuss with anyone if anyone has a questions. I hope it helps.
Yeah. Thank you. Questions, please, or comments? Go ahead, Paul.
Yes, Paul.
Well, thank you very much. That was really interesting to see decisioning at superscale. I was a little bit confused. I got the impression that you were talking about the transaction fraud detection. Is that correct, or or is it the application for vendors to appear on Amazon? Is that?
Oh yeah. So sorry, I think I used a word which uh, was in we basically use every day, but the term transaction means any any traffic that comes into the system. Like it can be transaction can be a product listing request. Transaction can be an actual payment transaction. So if the fraudulent system is designed for particular use case, that use case is a transaction.
I got you. That makes perfect sense, because I would assume that a lot of the there's defense in depth would be the raison d'etre for fraud, and tracking vendor registrations would be the starting point, and the end user purchase transaction would be the almost the final sort of transaction you would want to be checking. So thank you. That makes sense. You're basically checking all of the above.
Yeah, yeah, that's true.
Okay. You almost did not mention anything about implementation. When you say ML, machine learning, you mean traditional machine learning tools, right? Supervised or unsupervised or both?
Uh, so sorry, I didn't get your questions. You're talking about
Supervised machine learning, when you have historical data analyzed or not, or
Yeah.
unsupervised?
So we use both of them, like unsupervised and supervised. Based on the use case, we train them. Um, so the traditional machine learning is used to train the model, but the main architecture, it comes after that. Like the models are good at certain point, but when the scale comes into the picture, we have to create a multi AI agent architecture. That's where the challenges comes into the picture. Like when there is because it's a mesh of systems, right? So every system has couple of agents that have assigned task, and they have different permissions, they have different actions that they are allowed to do. There are different MCPs. MCP is like one of the way agent can do things, interact with systems, and actually go and trigger the system. So that's where the challenge comes into the picture, like how this agent to agent communication happen and how that will be traced back to a data lineage, like how this whatever agent do in the systems, how we can control everything. And also the traditional model is giving us output to the agent. So traditional model is one piece which is straightforward, which has their own, it's sitting there deployed, and all the things are monitored for the model. But the agents, different teams have different agents, so we have to basically understand and observe where things go wrong. If something goes wrong, let's say some agent goes and um, if someone asks Rufus, say, hey, buy me um, like a mobile cover, and Rufus is inferencing it and say, okay, let me also buy um, like the, the mobile itself for that guy, then it goes into add to cart. So that we have to say, okay, which agent took this decision, where it came from. So those things are a little bit of challenging right now.
You have question on chat from Charlene. You can see it.
Let me check.
What kind of drift are you most regularly experiencing at that scale? And is that detrimental dysregulations?
What kind of drift we are seeing? Yeah, so at a scale, let's say we launch one model with an agent, and agent has started. Um, so basically, it's an experiment we have to do first. Like we gradually shift our traffic to that new system and say, okay, now this agent is doing an action and the model is giving an output. Sometimes what happens is after certain amount of dialogues, uh, our confidence score is very high. But when we launch into a different marketplace, the same system, our models start reacting badly when there is a vast amount of varieties. Because, for example, different marketplaces, different rules, and that's where the confidence scores start dropping. So that's the one use case. The second is the traffic is not predictable. Traffic is unpredictable. Some days, like Prime Day is one of the example as this peak traffic where there are a lot of sellers are selling a lot of goods and so many, it's a chaos. That's where the system degradation happen. It can be in the agentic architecture, or it can be in the model because our sample size increase and we realize that okay, these are the thing that model is not or accurate on that part. So the scale measures comes with what's the traffic, what's the current traffic, and what's the traffic pattern. Sometimes what happens is bot start scrapping different websites because sellers typically have the third party contract with other people who just start scrapping websites to identify which product they can sell, and all the competition is going on. So they basically find different residential IP rotator, and there are so many things they find which also affect our traffic pattern and our model decisioning. So there are so many external factors that can what what is the confidence score right now and how the framework is able to react to that.
Okay, Tejas, thank you very much. You bring key experience from super scale applications. Not many of us have such experience, and it's nice to hear that decision intelligence techniques work well on such super scale. And thanks again for sharing your experience. Thank you.
Thank you.
Okay.